Have you ever held a piece of gold? Not just any jewelry, but a real solid gold bar. That incredible weight, that unmistakable gleam. It feels like you're holding a piece of the sun. But have you ever wondered how we get from raw, dusty, or dug out of the ground to these perfectly pure, stamped bars worth millions? It's not magic. It's a fascinating blend of ancient alchemy and modern science. Today, we're pulling back the curtain on the incredible journey of gold, from dust to billions, and exploring the science behind gold bar purity. So, grab your safety goggles, because things are about to get elemental. Let's start at the beginning. Gold doesn't just appear in neat little nuggets, although that does happen sometimes. Most of it is microscopic, scattered within tons of rock. Miners blast and crush this ore into a fine powder. The first challenge is separating these tiny gold specks from all the other worthless rock. One of the oldest methods still used today is called gravity separation. It's pretty simple in concept. Imagine you have a pan of sand with a few heavy pebbles in it. If you swirl it with water, the lighter sand washes away, leaving the heavy pebbles behind. Gold is incredibly dense, 10 times heavier than water-sew techniques like sluice boxes and shaker tables. Use water and motion to let gravity do the work, separating the heavy gold from the lighter rock particles. It's an effective first step, but it's far from perfect. It only gets the bigger pieces. To get the truly microscopic gold, we need to turn to chemistry. This is where things get really interesting. The most common method for extracting microscopic gold is called cyanide. Now, the word cyanide might sound scary, and it is a highly toxic chemical, which is why this process is done under extremely strict safety protocols. Here's how it works. The crushed ore is mixed into a watery solution, and a small controlled amount of sodium cyanide is added. In the presence of oxygen, the cyanide selectively dissolves the gold, forming a gold cyanide complex that stays in the water. The rock and other minerals are left behind. Think of it like making a cup of tea. The hot water dissolves the flavor from the tea leaves, but leaves the leaves themselves behind. Here, the cyanide solution is our water and the gold is our flavor. After the gold is dissolved, the gold-rich solution is separated from the solid waste. Then comes the next trick, getting the gold back out of the solution. To do this, they add zinc dust. Zinc is more reactive than gold, so it essentially kicks the gold out of the cyanide complex and takes its place. The gold then precipitates, falling out of the solution as a solid sludge. This sludge, called cement, is then collected. It's a messy, dark powder, but it's rich in gold. We're getting closer, but this definitely doesn't look like a shiny gold bar yet. This initial product is what's known as d'or. It's a semi-pure alloy, mostly gold and silver, but it still contains other pesky metals like copper, zinc, platinum, and palladium. It's valuable, but not pure enough to be investment-grade gold. To get to the famous 4 nines, or 99.99% purity, we need to refine it. There are 2 main industrial methods for this, the Miller process and the Wohlwill process. Let's talk about the Miller process first. It's faster, cheaper, and used for the bulk of the world's gold refining. The door is melted in a crucible, a special pot that can withstand intense heat. Then, pure chlorine gas is bubbled through the molten metal. What happens next is a beautiful example of chemistry in action. Chlorine loves to react with most metals, but it's not as fond of gold. It reacts with the silver, copper, and other impurities first, forming metal chlorides. These chlorides are less dense than the molten gold, so they rise to the surface as a slag, which can be skimmed off. This process continues until pretty much all the impurities are gone. The Miller process is great because it can produce gold that's about 99.95% pure, which is fantastic. But for the absolute highest purity, the kind needed for electronics and official monetary standards, we need to go one step further. Welcome to the Wohlwill process, the gold standard of gold purification. This method is a type of electrolysis. Imagine a bath filled with a special acidic solution, specifically chloruric acid. 2 electrodes are placed in this bath. The anode, or the positive electrode, is made from the 99.95% pure gold we got from the Miller process. The cathode, the negative electrode, is a thin starting sheet of pure 99.99% gold. When an electric current is passed through the solution, the gold atoms on the surface of the impure anode dissolve and enter the solution as positively charged ions. These gold ions are then attracted to the negatively charged cathode. They travel through the solution and plate themselves onto the pure gold sheet, atom by atom, growing the cathode into a larger mass of ultra-pure gold. So where do the impurities go? The remaining trace metals, like silver and platinum, either do undissolve in the solution or they fall to the bottom of the tank as a sludge. This sludge is actually super valuable as it contains platinum group metals which are then collected and refined separately. The Wohlwill process is slower and more expensive, but it's the only way to achieve that coveted 99.999% purity, often called 5 nines. This is the top-tier stuff, the best of the best. Once our gold is ultra-pure, it's time to make the bars. The pure gold is melted one last time, often in an induction furnace, which uses powerful magnetic fields to heat the metal without any direct contact, ensuring no new impurities are introduced. The temperature is carefully controlled because molten gold can actually dissolve gases from the air, which could create tiny bubbles in the final bar. Once it's at the perfect temperature, the glowing liquid gold is poured into precision-molded graphite casts. Graphite is used because it can handle the extreme heat and has a very smooth surface, which gives the bars their clean finish. The gold cools and solidifies surprisingly quickly. Once cooled, the bars are cleaned, sometimes quenched in water, and then weighed with incredible precision. The final step is the stamping. Each bar is marked with its weight. Its purity like 999.9, the refiner's official seal, and a unique serial number for tracking. This isn't just decoration. It's a guarantee of quality and authenticity recognized all over the world. From a simple cast bar to a globally accepted store of value. So why all the fuss about purity? For investors, 99.99% pure gold, or 4 nines, is the international standard for what's called good delivery bars. These are the large 400-ounce bars that are traded between central banks and institutional investors. Their standardized purity ensures trust and fungibility in the global market. You know that a bar from a refinery in Switzerland is the exact same quality as one from Canada or Japan. For industrial applications, purity is even more critical. In electronics, gold's incredible conductivity and resistance to corrosion make it essential for connectors, switch contacts, and bonding wires in our smartphones, computers, and countless other devices. Even a tiny impurity could disrupt the flow of electricity and cause a device to fail. In medicine and dentistry, its biocompatibility, meaning it doesn't react with the human body, makes pure gold ideal for certain implants and dental crowns. So that obsession with removing every last atom of another metal isn't just for show. It's what makes gold one of the most versatile and valuable materials on Earth. From a microscopic speck of dust hidden in a mountain of rock, through chemical baths and electrified solutions, to a perfectly stamped bar of shimmering metal, the journey of gold is a testament to human ingenuity. It's a process that combines raw power with delicate chemistry, turning chaotic nature into perfect order. The next time you see a picture of a vault stacked high with gold bars, you'll know that each one represents an incredible scientific journey. You'll know that the shine isn't just a reflection of light, but a reflection of centuries of science, engineering, and a relentless pursuit of perfection. Thank you so much for joining me on this deep dive into the world of gold refining. It's a subject that's as rich and fascinating as the metal itself. If you enjoyed this video and learned something new, don't forget to hit that like button and subscribe for more adventures into the science behind our world. Let me know in the comments what other materials or processes you're curious about. Until next time, stay curious.